Single view modeling. On this lecture, we want to describe how can we model a single view. You understand that we already have the system coming basically from a 3D space. So I have here a 3D space, and the 3D space may have a house, may have a, let's call it a car here. Now, these cars are 3D as well, so you can imagine we have this car 3D, the house is 3D, and then I will come here to an image, and this image are basically a 2D. So based on where I will position the camera and how this camera will interface with this domain or this dimension, I will be able to basically model the single view. So we have to talk about how we can map 3D space into 2D dimension, and this 3D space and 2D dimension is the key of this particular session. This session, as I said, it's always available on a podcast, so if you cannot have the PowerPoint slides, you can always download the audio podcast with the PDF file. If you can see the video, it will be great. This is Wael Badawi, and I will be guiding you through this particular concept.
This video. To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
So if we come to a single view modeling, as you see here, you have a 2D of a wall with two individuals standing with balloons. There is this particular reading, which is you can always go back and check. This view here, the question is, which one of these two individuals are the correct size or the right size? The other thing is she tall enough to reach the ceiling, or is she that short to be almost half of the window height? And you can see the clock on the back. So this particular example is called the Ames room, and it's a very common example we see in when we talk about video. I would like also to remind you that this particular content, you may came across it if you studied descriptive drawings or engineering drawings, and you understand how you can actually draw images and how we can do engineering drawing, and it's a like you will understand lots of mapping between 3D and 2D. So if I look at the actual room here, you will be able to see here that this is the point where you see the image. The actual location of the first subject is actually right here, and this subject is literally the girl with the balloon, and then it appears to you that it's standing at this point. However, the actual and appearance location of the second subject, which is the one to the right hand side, will be here. So if I want to understand why do we use this room, we use it in the following description. So if I go to slide 6, you will see using it for drawing, for measurement, for mathematics, for projection, for so if I want to draw 2D to 3D, which is usually in if you are in engineering major, you most likely you have an engineering drawing in the first year or so, where you'll understand lots of concepts coming from here. You also want to do measurement. So if I want to do an automatic measurement, how will we be able to proceed this automatic measurement? You can do it for changing projection. You can understore the images. You can estimate where is the camera. And moreover, the most important part is the object recognition, which basically you can detect objects. This will lead us to what we call it projective geometry. So if you see a 3D view, the 3D view, usually it's mapped to 2D, or the 3D space is mapped into 2D images. So here on the right hand side, you can see the music room. And the music room, based on the, if I understand the projective geometry equations of it, I will be able basically to estimate the 3D here to the top, or and the lower here, this is another view as well. You may notice in the 2D image there is this particular screen here, and this particular screen here, this particular part here have been removed because it basically it can actually estimate what's behind it as well based on this equation. So if I want to make images in the measurement in the, if I want to make measurement in the images, what I'm looking for here is papillary distance, which basically, if I have a face here and this face has two eyes and this eye has a pupils in it, the distance between these two, this distance here, this is what I'm looking for, and this is what we call it papillary distance. Because as you understand from before, we spoke about the pinhole camera, and we said that the eye itself has a lens and has a cornea, and the image formation will be here. So you basically have two eyes. Let's call it this eye, and there's the second eye here, and both here have 2D images. So you have an image here and you have an image here. So the distance of forming these images, it can help us using the measurement. In stereo vision, there's a very famous field which called it disparity distance, which basically you can measure the difference between this distance. So if I understand the projection, if I understand the plane, I will be able to measure this particular distance. So if I move to the next slide, you have here a hallway or a corridor, and these corridors will have different objects, and here I want to measure these objects. You have to you may understand that these tiles here, these tiles are supposed to be square. However, the tiles here are not shown as a square, so the distance here between these two tiles are different than the distance over here. Even the angle here is supposed to be perpendicular, because the tile, usually the tile, if I look at the tiles from the top, you'll have a floor like this, and then we have, let's call it here, 9 tiles. They are equal sizes. So if I wanna look at the floor in this image, I will be basically seeing, let's call it as well, 3 tiles. They are looking like this. So these tiles are not square, are not perpendicular angle. So if I want to measure, you may notice that the measurement here will be much bigger or much longer than the measurement here. The width here is different than the width here. So if I understand where is the camera and how this camera is seeing this particular room, I should be able to do some measurement, and then I will pick up some corners at these particular lines and figure out the measurement based on the cosine angle or based on some kind of angular descriptions. So this one here showed you if you want to unwrap the measurement, to get it an actual measurement, you have to get the projection, you have to correct the projection of the tiles to be able to get this particular measurement. And similarly, if you want to get measurement to the ceilings or the walls, you have to do the same, because the measurement here in blue is different than this measurement. So if I look at both angles, if I look at both equations, I will find out that x, y, and w are the same as s, x, sy, sw, which basically this is the new one. So if I want to do this mathematics, I will basically I will look at the line in projective plane, and I will apply with both equation, and then I will figure out the w, and I will figure out also the s as a coefficient for the transformation. So if I understand the equations in this way, I will look at the Euclidean space, and then I can compute the value of w, and then I can compute also the value of either x, y, or s, x and sy. So a line L is homogeneous in 3 vectors, and it is perpendicular at every point to the ray. So the perpendicular to the line is usually equal to 0, because the cross product of the two perpendiculars are usually the angle of them, the cosine of them usually is equal to 0. So if I understand the projections between P1 and P2, I should be able to find out that the line supposed to come from P1 and P2, they're supposed to be perpendicular. So in this way, they can be interpreted as a plane. So the intersection of these two lines can be computed as this equation here, and from that point, this line has. So if I have an image plane, the image plane will map indefinitely, and it could be a parallel to it. However, we only look for the image plane from a single point, and then the ideal point usually is the point which is parallel, and the ideal point parallel to the image plane that correspond to the line, it's a finite coordinate, and we have to go through the origin. These concepts relate to the 3D, and in 3D we look also at the homogeneous coordinates. And remember, in the homogeneous coordinates in previous lecture, we explained that we add the coefficient 1 or the coefficient w to be able to do the math in the proper function, and then the plane n will be represented into four vectors, or a vector of 4 elements, and the point in the plane also, they are perpendicular. So if I look at the projection here, I will find out that the projection of the line wx, wy, and y, which basically is a line, if I go to this 3D space homogeneous with 1, and I have the transformation matrix, the results will also be the line itself. You have to understand that if we preserve these lines, we don't preserve the angle. So if I have the horizon, I will be looking at, and then I will reach what we call it vantage point. We demonstrate the vantage point when we talk about railroads. So if I look at a railroad, you will see the railroads basically are meeting to a vantage point. So if you look at the railroads like this, you will find them, they meet to a vantage point. So we call this point at the horizon is the vantage point. To demonstrate the vantage point, I have the camera center, I have the image plane, and here is the ground plane, and then I will be able to locate points getting through the eye or the camera itself, and these points will be able to look at different ground plane, and all of these points which does not vanish, they will vanish at one point into the ground plane. And the vanishing point is where these rays will meet the image plane. So basically I have an eye here, which is the camera. I have here the plane of the image itself. I have here the 3D space, and this 3D space, if I will go and say I have a point here, so this point will vanish at the camera, then this point will also vanish at the camera, and then this point will also go vanish at the camera. So if I look at the space here, and this is the actual plane, I will find out that this particular distance will map to this distance. This particular distance will map to this distance here. So this mapping or this projection to infinity can often project it to a finite point in the image, and this point can be basically intercepted. So if you look at it from here, from the top view, you have the camera center here, then you have the image plane, and then you have the ground plane, and then each point from here will go through this particular vanish plane, and this will be the inside the vanishing point into 1D. Now if I move to the next slide, I will see vanish points into the 2D. So I have the image plane, I will have my own line, and then it will draw a line similar to the line I have it here on the screen, and this line will become the vanishing point. So how to determine which line is the scene vanish are given to a specific pixel? I basically will have two lines. Both lines will go to a vanish point, and any two parallel lines in the 3D will usually have the same valid point. The ray between from C to V is parallel to the lines, and the image may have more than one vanishing point. In fact, every image point is a potential vanish point. So what we want to say here is, if this is a vanish point, all parallel will be vanished to this point. You may have more than one vanish point. In the next slide, we will show the 1 point perspective. So from this perspective, I will have all parallel lines here are vanishing to a single point towards the end. In in drawings, we also studied the 2-point perspective, where the image will vanish into two different points. So I can have two vertices, and these two vertices where all parallel points will vanish to the closest one. I also can have what we call it 3-point perspective, where I will have 3 vanish points, one at the top, one at the side, and one at the other side. Based on which one you have, you will be able to find out how to map the real 3D into these images. Please, if you have any questions, let me know via email, or you can always put it in the comment below. And what we described till now is how to describe. We have a 3D space, and this 3D space, to map it into 2D, we talk about one vanish point. We talked about models where you have 2 vanish points, and you talk about three vanish points. And this is our models where we have basically the camera here, and then the plane of the image, and which one of these will map to this particular plane. So I want to describe here what we call it vanish line. So when we have more than one vanish point, and all these vanish points will map to one line, any set of parallel lines in an image will map to a vanish point. So here you have 2 sets. One is this lines here was supposed to be parallel, and then the other one. So this will be basically 2 vanish points, V1 and V2. The union of all of these vanish points will form the horizon. So the horizon is called the vanishing line, and basically the horizon is where parallel points will end up to be where parallel lines will end up to be 1 point. The different planes can define different vanish lines, and we can also define the multiple vanish point here define a vanish line. So it can be any kind of line. In the next slide, we will talk about how to compute vanishing points. So if I have the plane here in blue, I have the camera here, and this is the center of the camera, and the space, the plane of the image here. So the vanish point is basically where this point will intersect with the center of the camera. So this point, to describe it, it comes from the 3D space. So I will have bx, py, and pz plus tdx, tdy, and tdz, and we have 1, because this is the best representation we have, is to augment it by 1. And then I will compute, because I need to compute that's b. So if I assume that's p equal to p node plus tdx or plus td, so I will form the p 1 as a differentiation of tdx, and then p node will be dx dy. So the properties here I have that v will be equal to pi b infinity, and p pi is the point at infinity, and v is the projection, which basically is the location here, and it depends only on line direction. So the parallel line p plus td and p1 plus td, they intersect at p of infinity. So if I wanna, on the second slide, compute the vanishing lines, I will basically say if I have 2 lines here, and these 2 lines will actually vanish at 2 different points. So it intersects with the horizon, with the horizontal plane through C in the image plane. I can compute I from 2 sets of parallel lines, and from that point, all points of the same height as C, it will meet at this particular line. And we will study in the lecture, in the laboratory, in the tutorials, more mathematics about that. So I can compute using this equation here twice at both points. I can compute the properties. So if I have somebody who's coming into a parachute, so the question is, this parachute is lower or higher than the person taking the photo. So this parachute basically is lower than the actual horizon, and I can have fun with vanish points. So for example, here you have different people coming in, and they may look as different sizes, and this is where we talk about illusion. So people close by, away from the vanish point, will have different sizes. I can also look at different vehicles, and these vehicles are basically the same size, however they appear much different sizes. To illustrate this issue, I can show you here that if I have 3 objects or 3 subjects, and all of them are mapping to specific parallel lines, they look the same. If I change the vanish point, they will appear in a different sizes, and if I will do it here, they will appear on different sizes as well, where the closest to the vanish point will be smaller. So here I have my vanish point, and I can see that the same object will have different sizes. If I want to measure the heights, I have to invert this guy back to the specific sizes by knowing the equations of the equations we explained before, and then we figure out what heights does he have, and from that point we can do that. So, and this is, if I want to look at the turtle, it will be something similar. So if I understand the 2 lines, I can actually compute the measurement here. And this is related to how high is the camera, and this is actually the vanish line for both. If I want to compute the vanish line from the vanish points from different lines, I will have P1 Q1 which intersect with P2 Q2, and this is the intersection equation. I will have the least square version of it being proposed by Bob Collins, where he will use you have a height and you have a height h, and you have a ruler r, where basically you can compute relative distance, and then if I want to measure it without a ruler, I will compute the measurement from the image z, and then I will need more than one vantage point, and I will use the projected invariant as a vantage points. And from that point, because I have here 4 vantage points, I will basically look at 4 different lines which intersect between these vantage points, and then I can compute the mass of it. And I quite notice that here I will have 4 points, so I have a permutation of 24 different orders. However, I have only 6 distinct values for this particular one. Here is the measuring the heights. So if I have a reference point, if I have the top objects, if I have the bottom of the object, and I have the ground plane, I can always measure the heights by doing the projections across of the scene. And here is the ratio difference between the heights and the objects, and as long as I have this ratio, I can actually compute the mass of it. So here is the image cross ratio, and I can do the computation as well. So here I have this particular object in 2D, and it vanishes into 3 different points, and I want to find the vertical vanishing points. So if I want to measure the heights here, I have the h, I know the bottoms, I know the tops, and I have the r, and then from that point I can measure r relative to h, and h relative to r is the ratio, or the image cross ratio point. If the object will appear over a box, now the b will be changing, so I will have another m here, and this will actually change the whole mass for me, and then I have to map the size here to another vantage point. I understand it may be confusing. However, what you need to understand is whenever you need to compute the distance or to measure an object, you must consider having a new vantage point where you can apply the equation and get it. In the next slide, we'll talk about 3D modeling from a photography. So if I have an image like this, I will basically show you how you can compute 3D model out of this particular image. And what you see right now on the screen is basically how you can convert one single image into a 3D. It's for sure it's limited 3D because it's based on what exactly you can see in the 2D. So you can always, like from the right hand side, you can always extract the 3D images as well. Here is a video of the 3D images of this particular 2D image, and it has been constructed again using the same equations and have been repeated to every single corner, and then the colored is mapped. So now you can do the 3D morphing of the 2D image. The black are missing details. However, it's very close to a full 3D model. So the way it works is, as I said, is like basically you can get from different points or different corners. We now understand what's corner and edges. You can get and you can compute the vantage points, and then you can reconstruct the 3D. Out of this particular topic, we have to move to a related problem, and the related problem has to do which is camera calibration. So when I look at how to estimate the camera parameter, I want to solve the projection of the camera matrix. And if I want to understand the camera parameter, if I have, there is in camera's parameter, there is 3 different characteristics, but two mainly. One is the intrinsic one, which basically is the focal point, the principal point, the pixel size or the resolution, and one which is the extrinsic one, which basically is the rotation angle, the translation, the position of the camera. And I have also the radial distortion, which explained in the lenses before. So if I have the projection matrix here, and I have here 4 parameters, I can form the projection matrix into 3 different vectors. And the projection matrix, the by 1 will give me the vanishing point, and for by 2 I can get the vanishing point of 2 and the vanishing point of 3, and so this will be the different vanishing points Vx, Vy, Vz. So it's not so fast, because you basically want to it takes some time to compute, and when you talk about scaling, it will be A Vx, B Vy, and then C Vz, and we can basically provide 3 reference points, and we can compute all of these coordinates. So if I have this equation here, and this equation will have A, B, C as unknown. If I define 3 different, if I have the space here, and the space is mapping into a 2D image, and if I have 3 different points, and I know where are these 3 different points, I literally can provide a calibration to the lens, the camera itself. So using calibration, using a reference object, in the next slide, it's a very common approach where we can understand, we know the distance between each one of these 2 pixels, and we can basically extract the geometry from here, and from that we can estimate the parameters, and we have to understand the geometry in a very accurate way, and then from that we can extract the 3D from the 2D image, and this will give us the equation. This is here another example where we can look at how we can map the 3D into 2D. This is another examples here where we have different codes, and from these codes we can map the point. If I want to understand the mass behind it, I basically have 2D points here, and each one of these 2D points is a matrix coming out of a 3D point space. So if I identify the corresponding points to this image, I will be able to calibrate the camera itself. So here we have the linear calibration, where U, V, and 1, and this is the matrix, and here you have X, Y, Z. And from that we would like to understand the unknowns, and the unknowns is M00, M10, and M20, all the way to M23. And if I know these unknowns, I will end up having these equations here, and then by applying 3 points I can basically solve this equation, and I can use icon vectors, or I can use advanced mathematics techniques to solve these equations. The advantage of direct linear calibration is very easy to formulate. However, it does not tell much about the camera parameters. It doesn't model the camera distortion. It's hard to impose constraints, and it does not minimize the right function error. For the reasons, nonlinear methods are preferred. However, it's kind of difficult. So here is we have a multi-plane calibration, where basically we use the same screen and we move it different places, and we move it different orientation, and from that we will be able to map the points to each other, and then we can map it to we can extract the camera parameter. There is a OpenCV MATLAB version, and you can also refer to the websites in front of you here if you want to understand the math. There are other techniques to calibrate, which is existing in this particular slide, like image-based modeling and photo editing. There is a single view modeling and freeform scenes. There is a tour in a picture. Single image into depth prediction also can be made through a heat map, and this is our heat maps of the camera, or depth maps, and this is I can understand the depths. So if you have any questions, please send them to me via email or write them down here. The question is, what did we get today? Today we understand a little bit about mapping 3D space into 2D, where we look at one vantage point or two vantage point or three vantage point. We review there is some kind of equations where we can, if we know the 2D, we can construct the 3D back. We can also use the same concept for camera calibration and understand the camera parameters. And this particular understanding will allow us to extract the camera parameters. If you are concerned about the exams, usually you get one of these equations and it will ask you how to do the techniques. You don't need to memorize these equations, and you don't need to understand more than the actual theory of having this parameter extracting by having some unknowns, and then you can solve the equations. The exams usually are very short to have a large problem to be solved. This is the location for the tutorial or the lab where you can find out more about how can you extract or how you can compute such parameter. I would encourage you to play this video again and review it. If you have questions, just email me, and looking forward to hear from you.